Okay, there's a chain of Ainsley oscillations, but this time we're looking at something a little bit different. Instead of looking at the common drain trace here on the B trace, instead what we're looking at now is the voltage drop across the current viewing resistor, the so-called shunt. This up here is the signal coming from the 555 timer. It's an all negative going pulse. I'm sorry, I've got the 0 setting in the wrong place. It should actually be right there. Let me turn off this trace for a moment. Sorry. Okay. Just turn the A trace on and turn the ground the channel. And I don't know if you can see it, but there's a little dot right there that marks the 0 line of this particular trace. Okay. So when I turn it on, you'll see that the top there is at that 0 line. See the gradical line back there underneath it? So this is a negative going pulse coming from the 555 timer right there. Okay, and that's going to the tar baby circuit with 5 IRF PG50 MOSFETs and the standard load running off of the 3 batteries. Nothing up my sleeve. The probe is looking across the current viewing resistor in the location that is marked channel 1 on this diagram right there. Okay, so that's the location of the channel 1 of the B trace, which is this trace. Okay, so the top trace is the signal from the clock timer, and then the bottom trace is, we'll just eliminate that. Now this trace then is the trace across the current viewing resistor. And what I've done is I've set the 0 line right at, I tried to, hang on a second, let me see here. Okay, so I'm setting the 0 line right on that center gradical marker. Okay, right there, right on there, right on the center. Okay, and we're looking at this at the knob is at 0.05 volts per division, so we have a 10x attenuating probe, so this is actually half a volt per division on the 0.25 ohm current viewing resistor. Okay, so now we'll turn it on, we'll look at those oscillations, and what I'm going to do is now change the time base so that we get a good zoomed in view of those oscillations. Okay, see that? Now current going around the circuit in the positive direction is up above the line, and current going around the circuit in the negative direction is below the line, like this. Okay, so not only are you going to have to be looking at the peaks, which are in this case just right at almost exactly the same, right? I guess you can see the radical. Okay, I've got it turned up all the way. So if I move it over horizontal, or no, I don't want to move it. Don't want to move it up and down. But if I move it horizontally over to where there's a peak right on this line with the divisions in it, we can see that we are 1 major division and 1 minor division exactly above the 0 marker line, right? So at half a volt per division, that's half a volt plus a fifth of half a volt, which is a tenth of a volt, right? So we're at 0.6 volts current drop across the current viewing resistor in the positive direction. Okay, now the bottom peak, same thing. We'll move the bottom peak over until we're right on a gradical marker, and we'll count down 1 major division and 1 minor division. So that's 0.6 of a volt, right? So we have the same peak current going in one direction in this AC oscillation as we have going in the other direction. Now, if we were able to multiply this trace by the instantaneous voltage trace coming from the drain, which I cannot do on this oscilloscope. I can't do that kind of math on this scope. Then we would get a trace where we would be interested in the areas between the top and the areas of the bottom peaks, okay? And the areas then of that instantaneous power trace, which is obtained by multiplying this trace by the instantaneous voltage trace, the areas of that trace then correspond to integrating over time, okay? And so then what you're looking, and of course then if you integrate watts over time, the answer is in joules, or energy over that period of time. So you'll be interested in looking at the areas of the power that's going one direction compared to the areas of the power going in the other direction. So unfortunately that's the kind of advanced math that I cannot do on this oscilloscope. But there's a way to get around it. One could actually, since the integral of the sums is equal to the sum of the integrals, one could actually integrate these traces separately. So I could take a piece of graph paper and I could put it over this screen and I could laboriously trace out this curve and then see how many little squares in the graph paper are in positive and negative zones. Or I could even, if I was really crazy and had the tools, I could cut out the wave shape from the graph paper and weigh it on an analytical balance to determine what the ratio of areas above and below that zero line corresponds to. Okay. Now right now it looks to me like if I were to do that, okay, hang on a second, let me see if I can put a little marker on there. So now I just turned the A trace display on, and what I'm going to do is just put that flat A line, even though it's not indicating anything, I'm just going to use it to mark where exactly the center of the gradical is. Right about there. Okay, so that indicates now where the zero voltage level is. So anything below the line is current flowing in the so-called backwards direction. Anything above the line is current flowing in the correct direction as far as the circuit is concerned. Okay. All right. So now it certainly looks to me like there's more area in the peak above than there is in the area below. So just roughly guessing, I would say that if I integrated this trace over time, I would see what would correspond to a positive energy flow, not a negative one. In other words, energy is flowing out of the battery, or in this case out of the 555 timer supply in these oscillations, and is going mostly around the circuit in the correct direction. But these oscillations are strongly dependent on the inductance in the circuit, and what I'm doing now is I'm just moving my hand around and mashing on the wires. I'm doing this, okay? And you can see how that changes the shape, the amplitude and the shape of the waveform a little bit when I do that, if I manage not to kill the oscillations totally. Also, by varying the power input to the 555 timer, I can turn those oscillations into almost a pure sine wave, which I think is really neat. If you get a lot of power into the 555 timer, you get more and more distortion until finally the oscillations actually stop and the MOSFETs begin switching. Why they begin switching, I don't know, but they do a little bit. Oh, 313013. Uh-oh, is the universe trying to tell me something? Yeah, I think it is. I think the universe is trying to tell me something. 92 degrees. Oscillations. Oscillations. Oscillation. Oscillations. Oh look, phase. Thanks for watching. Oh, phase. Phase. Thank you for watching.